Hello, everybody. So what we're going to be doing today is we are going to be finishing up section 6.6, which is surface integrals, part 2. Okay. So last time what we covered was parameterizing surfaces, which I didn't write here. I will. Parameterizing surfaces and surface area, basically. So what we did was we came up with a formula for surface area of a surface, which we said that was going to be this integral, double integral of ds. And in order to calculate the ds, you had to do a couple of things. You had to, number one, parameterize your surface. After you parameterized your surface, you were going to calculate these two vectors, which are tangent to the surface at a point. Once you have those two vectors that are tangent to the surface, then you're going to use those to calculate this magnitude TU cross TV, which is the area of a parallelogram determined by these two vectors. And then once you have that, you integrate the whole thing, okay, over appropriate bounds, which I just wrote S here. Okay, and that's what we did last time. Okay. So what we didn't do was actually integrate functions, right? There's no function in this integral. It's just ds. Okay. So this time we're going to do, what are we going to do? We're going to do surface integrals of scalar and vector valued functions. No, that's wrong. Um, of a scalar function. No, that's right. That was right. Scalar valued functions and vector fields. That's what we're going to do this time. Okay, so let's write that this time. Last time. Okay, so the way we're going to get started is scalar value functions. Okay, so scalar functions. All right, so I'm just going to jump in and I'm going to give you the definition. We're going to say the surface integral of a scalar valued function. I'll just say scalar f of, yeah, just scalar f would be xyz, but I'm just going to say scalar f over a piecewise smooth. We did talk about smooth parameterizations of a surface before, and we're still using them. So we have a piecewise smooth surface S and the surface integral, which is what we're calculating. Let's highlight that, is going to be double integral S, and we're just going to put the function and then ds, right? So what's the difference? The only difference is we're putting the f of xyz right here. That's all we're doing, okay? So we're integrating a function now instead of just integrating one. And then they say, and where did this come from? Well, it came from the exact same thing we did last time, where sorry, can't talk, do things at once here. I goes from 1 to n, j goes from 1 to m. I reverse those compared to the book. It doesn't matter, right? So the way we define all of these integrals is they're going to be something like this, and then you do a limit as m and n go to infinity, right? And we did this last time, except without the function here. So I'm not going to do it again. I'm just going to say this is what it is. Okay. Now the steps are for doing these integrals is going to be identical as what we did last time. So that's really kind of the punchline here that you need to understand. So steps for integrating, or I'll say for evaluating or setting up or everything a surface integral. of a scalar function, because we haven't looked at vector fields yet. So the steps are the same as what we did last time with one extra step, right? So what you're going to do is you're going to parameterize your surface, um, and I'll say as R UV. Then what you're going to do is you're going to compute. Remember, we're going to need the TU and the TV. And at some point, we have to do TU cross TV. But, you can do that in the next step. And then our third step was setting up the integral, right? Uh, and that's still the same. I should do this. So RU, right, is going to be, with bounds for U and V. All right, so we set up the integral. And so you're starting with f of x, y, z, right? And then ds. And then what you're actually going to have to do is you're going to have to do the double integral over, I'll say d. You're going to have to plug in your parameterization, right? We've done this before for line integrals. We're going to plug in your parameterization into the function. And then your ds is still the same ds as it was before. That didn't change. Okay. And then, of course, finally, you would actually integrate um, to get your answer. Okay. So the only thing that's really new is this right here, right? Everything else is identical to what we did last time. Only new thing. Okay. So because there's nothing else new here, then all we should have to do is wait, hold on a second. Let me see what they do here. Hmm. They write what we write. Oh, okay. I was confused for a moment. I was double checking here because they were writing R prime, and I'm like, what? Where did an R prime come from? What does that even mean? And then I realized that they were just referring to the line integral section to remind people of something. Okay, so let's do our first example of this. So this is going to be pretty straightforward if you did the previous lecture. So they say calculate the integral over s of 5 ds. So, 5 is not going to be that interesting, but here we go, where r of uv, they're giving us the parameterization, which is nice of them, u squared v, and then they say for 0 less than u less than 2, and 0 less than v less than u. Oh, okay, there's a wrinkle, right? We don't have a constant here. We have the variable. Okay. So how would we do this? Well, let's just follow our steps, right? So our first step would be to parameterize, except they did, so we don't. So they did it. The second step would be to compute. We're going to need the TU, the TV, and at some point that cross product, which we were doing on Wolfram last time because we were lazy, and probably we still are. All right, so let's write this. So we got TU. So you've got your components here, your X, your Y, and your Z components, and TU is going to be the partial with respect to U of all those things. So the partial with respect to U of U, of course, is 1. The partial with respect to U of U squared is going to be 2U. Partial with respect to U of V is going to be 0. Then we've got TV, where this is going to be 0, this is going to be 0, and this is going to be 1. So we're just going to get 0, 0, 1 for TV. we need the magnitude of the cross product. So we're going to need the magnitude of 1, 2u, 0 cross 0, 0, 1. At some point, we may as well do it now. That's something that's convenient to do on Wolfram Alpha. So it is cross. I usually open two sets of parentheses, 1, comma, 2u, comma, 0, comma, 0, comma, 0, comma, 1, parentheses, parentheses, closed. All right, so that's just the fastest way I know of to type that in. You can double check that it interpreted it correctly. And so my resulting vector is 2u, negative 1, 0. Now we need the magnitude of that. So usually what I'll do is I will just, click on the result here. It brings it up to the box. And then I just say magnitude. And if it doesn't do what I want, then I try to type in something else. See, it didn't, right? So it thinks U is some atomic mass thing. So I'll put an asterisk there, so maybe it'll interpret it as multiplication. It still interpreted it wrong. So then I think it doesn't understand that I've got a vector, and I think it does vectors with curly braces. So I'm going to try this. It just really doesn't want to. So at this point, right, when you're fighting with Wolfram Alpha like this, the issue is that it doesn't like the U, right? Like it says input interpretation to U. Well, no, that's not what we want U to mean, some atomic mass unit. So the easiest thing to do here is change the U out to a different variable. Like maybe I can use a Z there. And remember that that's the wrong variable though. So this time it interpreted it as a variable, which we wanted, and it gave us the result. Uh, and just remember that it thinks that the variable z could have imaginary numbers, and that's why it's using that weird notation there, like absolute value z squared. If you scroll down, it will have usually a version where it says if z is real. I don't see that here, so I'll just type it in. Anyway, what we want here is this is just going to be square root 4z squared plus 1. You don't need absolute value. That's assuming that z is complex. Oh, also, z is the wrong variable, right? It's actually u. I just changed it to u. Changed it to z. Okay, so we did that. We got the answer. I mean, that would have been, I don't know why I took that much time, right? I should have just done this, and then we would have been done in 2 seconds. But I didn't, so I didn't. Anyway, so we've got the magnitude of that vector, and so we should be able to set up our integral now. So our integral over s of f ds is, well, let's try to set it up. Leave some space. Our function is simply 5. That's kind of a stupid function, but it's the one we got. So 5, and then ds, and we know that our ds is actually this bit, so we need that magnitude tu cross tv, and then the dA. So 4u squared plus 1, and then your dA, which your dA could be either du dv or dv du. And if you look at your limits of integration, or you look at your bounds here, let me just duplicate that and bring it down to look at. When you're looking at this right here, when you see that v is between 0 and u, that means you're going to have to integrate with respect to v first, right? You can't do this 0 to 0 u, because then your final answer is going to have u in it. That's wrong. Right? If you've got a variable for a limit, it's going to have to go on one of the inner integrals. So it's going to be 0 to u, and that's the integral for v. And then the integral for u will come second, and that could be 0 to 2. Okay? So that's how you set that up. Now this integral here, well, first integral, well, you know what? I think I did every integral on Wolfram last time. So let's actually integrate this. Let's just, okay, step 4, integrate. Let's actually do one. So 5. If you're doing the antiderivative here, what you want to remember first of all is our first integral is actually the dv integral, which means this entire thing is actually a constant as far as the integral is concerned. So you just are going to carry this on along like it's a constant, 4u squared plus 1, and then you're just going to have a v on the end. And in fact, we could, if we were smarter, even pulled that all out to start with. And the only thing we're integrating is really the dv from 0 to u, and then du. So we plug in, so that's our antiderivative of dv is just v. We plug in our we plug in our 0. We're going to get 5 square root 4u squared plus 1 under the radical. And then we're going to integrate v, or not integrate, we're going to plug in u and 0 into v. We're going to have u minus 0, and then du, like that. So our integral becomes 0 to 2, 5 square root. Actually, no, this is fine, actually. 5 square root 4u squared plus 1 u du. So we have this integral to do. This, of course, is a regular substitution integral. What we want to do is we want to let u, actually, well, we can't use u, can we? Let's try w. Let w equal 4u squared plus 1. So then dw would be 8u du, right? To match that, u du. Move the 8 over, so we get du over 8 equals u du. And my integral will turn into integral. I'm going to leave the limits blank. I got a 5. I've got a square root, just w. This turned into a w because due to force of habit here, dw, dw. Yeah. So 4u squared plus 1 is going to be w. And then u du is going to be dw over 8, like so. And then our limits of integration, or sorry, our limits. The top limit was u equals 2. But if you plug that into your substitution, you get w equals 4 2 squared plus 1, which is 4 times 4 is 16 plus 1 is 17. So our top limit is 17. And if I do u equals 0 for the bottom limit, w is 4 times 0 squared plus 1, which is 1. So 1 for the bottom limit. Okay, so take the 5 and the 8 out. Then we have the integral from 1 to 17 of w to, or square root, well, yeah, w to the 1/2 dw. We have to do the antiderivative here. So the antiderivative is going to be w to the 3/2. Divide by 3/2, but dividing by 3/2 is multiplying by 2/3 from 1 to 17. So we end up with 5/8. Let's combine that with the 2/3 times 2/3. And then let's put in our 17 and our 1. So 17 to the 3/2 minus 1 to the 3/2. Which, do a little bit of canceling here. 2, like that. So our constant out front is going to be 5 over 12. Right? Yeah, 10 over 24, 5 over 12. 17 to the 3/2 is just 17 to the 3/2. And then the 1 is a 1. So this would be the exact answer. And it's just a number, right? So you could punch it into a calculator if you need the result. Of course, you could have done the whole integration process on Wolfram Alpha and saved yourself some time. So there we go. We set up one of these. So let us do one more. Okay, so let us, we're going to do one hard one. So we did one easy one. We're going to do one hard one. And this is going to be kind of hard. It's okay. We're smart. We can do it. Example. So they say calculate the surface integral of double integral s of f ds, where f is just going to be z squared. So that's easy. Um, and s is the piece of the sphere x squared plus y squared plus z squared equals 4. So that's a sphere radius 2, but it's above the plane z equals 1. And the disk at z equals 1 um, enclosed by the sphere, which is not going to be super understandable, but it will be once you see the picture. It will make sense, I guarantee it. So if you have a sphere and the radius is 2, right? So I'm just going to draw my sphere. So let me get that in the right place. Close enough. Okay, so there's our sphere, radius 2. Okay, so there we go. Now up at z equals 1, we have a plane, right? And so what's happening at z equals 1 is we are cutting off the sphere right here at z equals 1. And then the surface that we want is going to be this disk, the disk here, this disk, and then also, keep doing the wrong thing, also this part up here. So there's actually two pieces there. Okay, so we want both the part of the sphere above z equals 1, and then also that disk that you get when you cut it off as z equals 1. So like the base. All right, and then so that's what we want. So there's two pieces there. Two pieces there. Okay, and so that is what we want to integrate over. Okay. Now, that means we have to parameterize each piece here. Okay, so like if I call, I don't know which one's which. Let me look and see what the book calls which one which. They say the base is S1, so they're going to call this S1, and then the part of the sphere is S2. Okay, now S is not smooth, by the way, because there's like sharp corners there, but S is not smooth, which it's supposed to be, but individually S1 and S2 are smooth, so it's piecewise smooth. And that's all we need according to our definition, piecewise smooth, because you can just do the pieces separately. Okay, and what we'll have to do is we must actually do two integrals. The double integral over S1 of f ds, and we're going to have to do the integral over S2 of f ds. Okay, so we can do, each one. So let's try to figure this out. So let's do S1 first, which is the disk. So let's S1 first. It doesn't say first. S1 first, just because I feel like it. Okay, so S1 is simply like up here at 1, and then you've got a disk. Okay, so that's not, again, hard to understand or anything, but what we got to do is we have to figure out, like, what's the radius of that disk? Like, that's what we need to know. Okay, um, so to parameterize, we need to know the radius up there. So the way you get it is this: the sphere is x squared plus y squared plus z squared equals 4, right? And the way that we got that disk is z equals 1 on that disk. So if you plug z equals 1 into that sphere equation, you get x squared plus y squared plus 1 squared for z equals 4. And then you get x squared plus y squared equals 3. So that's what's going on here. Okay. Um, so then to parameterize that, here's what you would do. So S1 is x squared plus y squared needs to be less than or equal to 3, right? Because equals 3 is actually the border, and less than or equal to 3 would be the inside. And then the z value is just going to be constantly 1. So what could we use for our parameterization? So for a parameterization, we could use something like this. So we need an x, a y, and a z. So the z is the easiest. Z is 1. Okay. Now for x and for y, what you're going to do is you're going to use the polar coordinates parameterization. Basically, you can use r. You can call them r and theta if you want, or u and v is fine. So like I could do like u cosine v and u sine v. And then what you would do is u, that's your radius. So it would have to be between, right? U equals 0 is here, u equals, I guess, square root 3 is out there, right? Um, so u would be between 0 and square root 3. And then v, we're using v to be our angle, and we're going all the way around the circle. So that would be 0 and 2 pi. And if you don't like using u and v there, you can use r and theta. It's okay, but I like this a little bit better. Okay, so this will be our parameterization. So we did it. Okay, so yay. Now, once we have the parameterization, we can proceed here, right? We could calculate the TU and the TV just for S1, TU and TV. So TU is, right, we need partials of each of these with respect to U. So cosine V, sine V, and 0. TV, so partial here with respect to V is going to be the derivative of cosine V is going to be negative sine V. So negative U sine V, U cosine V when you take the derivative, and 0. Okay. Then we need, of course, to compute the magnitude of the cross product. So TU cross TV, which, again, I'm not going to do because I'm lazy, but I'm just going to tell you what it is. If you do that cross product, you're going to end up with 0, 0, u, not u squared, u, cosine squared v plus u sine squared v, and we need the magnitude of that. But u cosine squared v plus u sine squared v is just going to be u due to that identity we've used many times. And then when you do the magnitude of the vector 0, 0, u, well, that's just going to be u. Since there's only one component, right? Like what's the length of vector u 0, 0, u? I mean, it's just u. So there we go. So then we can set up our integral because our integral just over S1 of f ds is, of course, going to be a double integral over d of f magnitude tu cross tv ds with, let's figure it out. So first of all, where's my f? F was what function? Somewhere. Z squared. F is z squared. So f is z squared. So when you put that in for f is z squared, which is 1 squared, because at the parameterization, whoa, it just force closed on me. Let's see how much we lost. A lot. All right. So this magnitude was u. We're setting up our integral. Okay. So we're going to set up our integral, double integral over S1 of f ds was a double integral over f magnitude. Actually, I'm going to put that in. The f was z squared, right? And the magnitude of tu cross tv ds, and then that's d now. So let's figure this out. Z squared is 1 squared. The magnitude of tu cross tv is simply u. And then the ds, or not ds, it should have been dA, sorry. dA is du dv, whichever way we want to calculate it. It doesn't matter here, so let's just go du dv. And what are the limits for u and for v? So if we look, right, our limits for u and for v are right here. U between 0 and root 3, v between 0 and 2 pi. So 0 root 3, 0 2 pi. 0 root 3, 0 2 pi. Okay. So that's a pretty straightforward integral. I am just going to, I'm just going to tell you the answer here. This is a very simple integral, right? So step 4, compute the integral. And I'm just going to say that this is equal to 3 pi. Very simple integral to do though, right? Like this is u squared over 2, you plug that in, and then integrate v. So 3 pi. Now that's only for S1. So now we're going to do the integral for S2 because it's in 2 pieces. All right, so we need a parameterization of the sphere. Okay, so this is where you want to look this up. Okay, so we need to parameterize the sphere, just the portion that we care about. But if you look in the book, you'll find this. So from book, the full parameterization of, I'm just going to say x squared plus y squared plus z squared equals, I'm going to use capital R squared, is R of, they use phi and theta, is 2, no, not 2. For us, it's going to be 2, but in general, it's R cosine theta sine phi, comma R sine theta sine phi, comma, 2 cosine phi. And that looks like the spherical coordinates formula because it should, right? We're parameterizing a sphere, so it looks like the spherical coordinates formula. We change that to an r. Okay, and then this is going to be for theta between 0 and 2 pi. And because, again, this is like spherical coordinates, the angle phi is going to be between 0 and pi. That's the whole sphere, okay? For us, we get, so we're going to redo the same thing. However, r of phi theta, of course, we're just going to write this out using a 2 for our radius because our sphere is radius 2. Now, I know that our sphere was radius square root 3 for that disk, but we're not talking about the disk anymore. We're actually talking about this sphere with radius 2. So we got 2 cosine theta sine phi for the x component. Y component is 2 sine theta sine phi, and 2 cosine phi for the z component. Okay, now what about the bounds? Now for the bounds, we are going all the way around, like theta is all the way around the circle, right? So we're going all the way around the circle for theta. So that's going to be 0 and 2 pi for theta. So theta is going to be between 0 and 2 pi. However, the phi is not going to be 0 and pi because remember, the angle phi, when you're looking at spherical coordinates, where are we here? The angle phi is an angle from straight up to wherever you're going, right? Like, so straight up to straight down is pi. We're not going pi, we're only going from straight up to here, right? This is only a small section. Like, this would be like from here, you go like pi over 6, pi over 4, pi over 3, pi over 2, then like a little bit bigger than half pi, 0.6, 0.7, 0.8, 0.9 pi, right? So from 0 up to pi, this is pi over 2. So you need to actually figure out what this angle is. So if I just still this picture here, duplicate it, drag it down. Can't really resize it smaller, I don't think. But so the problem that we have before us is this. We know that straight up, of course, is phi equals 0. But this is phi equals, I don't know. And that's what we got to figure out, that angle right there. And it's not going to be super hard or anything because we can use we can do it in 2 dimensions here, right? If you just put like y right here and then you put like z right here, and we know that this is 2, and I don't know why I did the way I did it, but we know that the sphere has a radius 2, right? And then we know up here at 1 that if you come over here, we even found this distance already is square root 3, right? So if you've got this point right here, the x coordinate, or rather y coordinate, because I have y where x should be, is going to be square root 3, and the z component there is 1. Okay, so what we got to do is figure out this angle. Let's delete this. We're trying to figure out the angle from here. That's the angle that we want, right? And so you just pull out a triangle from here like this. Why straight lines? Come on, make a straight line. And then just from the geometry of the situation, this side is 1 because it's this side. This side up here is square root 3. This side here is 2, right? And then so if you were trying to figure out what this angle is, this one's a right angle, right? Then how would you do that? Well, what you would do is you would say, um, hold on, this is confusing me. Yeah. Okay. So the way you would figure that out is you'd have to use trig. So we could do it like in a lot of different ways. So like let's just say like what would be the sine of phi here, right? So normally the sine of an angle is the opposite side over the hypotenuse, right? Which if this is phi, then the opposite side is square root 3, and the hypotenuse is obviously the long side is 2. So you get that sine phi is square root 3 over 2. And then that would imply that phi is going to have to be sine inverse of square root 3 over 2. But you know where the sine is square root 3 over 2, right? That's going to be 60 degrees or pi over 3. Of course, you punch that into a calculator if we do not know it. So that angle must be pi over 3. So this is going to be 0 and pi over 3 once we figure that out. Okay, so you actually have to figure that out using the geometry of the situation. It's not always easy to do that, but you learn these tricks from doing problems like this one where we figure it out. Okay, now once we've got the parameterization, we're able to move on and set up the integral, right? So we're going to need to compute the TU, although in our case, it's not going to be TU, it's going to be T theta and T phi, because that's what we got. And let's do that. So what's T theta? Derivative with respect to theta. So find our parameterization. Okay, it's up at the top. Um, so take the derivative with respect to theta. The derivative of cosine theta is going to be negative sine theta. So we're going to get negative 2 sine theta sine phi, comma. Take the derivative of the second component with respect to theta. We're going to get a cosine theta there. So 2 cosine theta sine phi. And then the derivative of 2 cosine phi is 0 because there's no thetas. Now we got to do partials with respect to phi. Very similar. So derivative of sine phi is going to be cosine phi. So we're going to end up with 2 cosine theta cosine phi, comma. The next one is going to be negative 2 sine theta cosine phi. And then the derivative of 2 cosine phi is going to be, wait, that should have been positive 2, sorry. Positive 2 sine theta cosine phi. Both of those we're taking the derivative of a sine phi. All right, last one. The derivative of 2 cosine phi is going to be negative 2 sine phi. Okay. This looks like a good place to use Wolfram. So we want to do magnitude of Tu cross, or T theta cross T phi. All right. Now, in order to do this, I would definitely recommend like that you change your variable names. Come on, let me zoom in. All right, we got to do a cross product. Cross, parentheses, parentheses. All right, what do we got? We got negative 2 sine. I'm going to use T for theta. And then I'm going to use a P for phi. So negative 2 sine T cosine T, comma 2 cosine T sine P, 0, close, comma, open up another one, 2 cosine T cosine P, comma, 2 sine P cosine P, comma, negative 2 sine P. All right, so I think I typed that all in. one more parentheses. You should double check that you typed it in right. We get a lot of nonsense there. Let me just double check this. Whoa. They actually have a different answer than me. Let me just double check these. 2, 2, -2. Okay. -2, +2, 0. Okay, no, that's fine. Oh, okay. They just reversed the order that I used them in. Okay, so yeah, these are right. Okay. So what you get here is -4 cosine theta, right? Remember, sine squared phi, comma, -4 cosine phi, sine phi, sine theta, and then my last component, which is um, they didn't simplify, but can be simplified. Let me scroll. Ooh, I should have just done that. You know what? This is going to be too long to write here. I don't want to write that all out. I'm going to do vector length. Vector length right here. Okay, so according to your book, where this ends up is that this is going to be the magnitude of 16 cosine squared theta sine to the fourth phi plus 16 sine squared theta, but I wrote a phi, sine squared theta sine to the fourth phi. Not enough room here. Let's move this over. Plus 16 cosine squared phi sine squared phi. Okay, so then they take this. There's a sine squared and a cosine squared, right? So like you can this and this can be factored out because the rest of it's the same, and you'll end up with 16 sine to the fourth phi. Um, yeah, 16 sine to the fourth phi plus 16 cosine squared phi sine squared phi, like that. They both have a 16 that can be taken out as a 4. And then I guess we're just going to have sine to the fourth phi plus cosine squared phi sine squared phi. And that's just what that is. Okay. So that's what we get. So once we get that, and again, I just looked that up in the book. We could have probably gotten it from the computer. Our integral then is a double integral over S2 of, f ds, which is going to be double integral over, what do we got? We have z squared, right? And then this magnitude of tu, although in our case it's t theta cross t phi, and then dA, which is going to be d theta d phi, which when we do that, so z squared, what's z squared? Z squared is from our parameterization, right? So z is right here, 2 cosine phi. So that actually gets plugged in for the z. So 2 cosine phi squared, like that. Um, yeah, that's right. Then you've got your magnitude, which is 4 sine to the fourth phi plus cosine squared phi sine squared phi. And then your dA, by the way, so remember how when we did spherical coordinates and polar coordinates, you had like the area element dA, and it was like, like r dr d theta, or, there was a more complicated one for spherical coordinates. We're not doing that here because we didn't actually use spherical coordinates. We just used a parameterization that looked like spherical coordinates. So the dA is just a normal d theta and d phi. Okay, so don't let that confuse you, right? We're not really in spherical coordinates, although it looks like we are, right? We could have used u and v's for our letters, and we just didn't. All right, so limits of integration, theta we know was 0 and 2 pi, and phi we found was 0 and over 3. So there we go. Now we got to integrate this. So a little bit of work here. I'm going to do a little bit by hand, not very much. 2 squared is 4, um, and 4 times 4 is 16. So we have 16 integral 0 to pi over 3, 0 to 2 pi. We got cosine squared phi, square root, sine to the fourth phi, cosine squared phi, sine squared phi, d theta d phi. Now, we're going to do the integral first, theta. We're doing the theta integral first, and there are no thetas. So all of this is just a constant as far as theta is concerned. So really, we're just going to integrate d theta, which will go to theta, from 0 to 2 pi, which of course is 2 pi, right? So when we do that first integral, we're just going to get a 2 pi, which I can combine with that 16, and then we really got the integral from 0 to pi over 3 of this, right? There were no thetas, is my point. And so I'm just taking a shortcut to write the answer for that first integral without doing much of it. Okay. All right. So this is the integral that we have. You would have to figure out how to do this. How would we do this? Let's think. Um, you would, first of all, you would take this, you would write it as sine squared phi, and then you'd have sine squared phi cosine squared phi. I missed this is written incorrectly. At some point, I stopped writing a plus, 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 plus. All right. So you can write it like that, right? Because they both got they both have a sine squared. And then if you do that, you can have 32 pi, integral from 0 to pi over 3. You got your cosine squared phi. We're going to take this sine squared out as a sine phi. You got your square root. It's just in there sine squared phi plus cosine squared phi now, which of course is 1. So we just have the integral from of 32 pi, integral from 0 to pi over 3. We just have simply cosine squared theta sine phi d phi. So it actually becomes relatively simple once you get to that point, right? Like look up here before I made the mistake. Uh, right, you can see the sine squared. Sorry, you can see the cosine squared, and there's a sine squared here if you take away 2 of the sines, which is what we did in the yellow. Okay, so you end up here. Now, this is just a U-substitution integral with u equals cosine phi, du is negative sine phi d phi. So you substitute that in, we got 32 pi integral u squared and then negative du. And then your limits of integration, if you put a 0 into cosine phi, cosine 0 is 1, you get a bottom limit of 1. You put pi over 3 in here, cosine of pi over 3 is 1/2. We get 1/2 up there. So we end up with negative 32 pi u to the 3 over 3 from 1 to 1/2. So we end up with negative 32 pi 1/2 cubed over 3 minus 1 cubed over 3. I'm going to change that to a positive 32 pi and then reverse these. So the first one's going to be 1/3 and then minus, this is 1/8 over 3, which is 1 over 24. Something happened. Oh, they made a mistake. They made a mistake in the solutions. That's what happened. They put a pi over 6 in the solution. Interesting. All right. So 1/3 minus 1 over 24, that's 8 over 24, 7 over 24. So I get 32 pi 7 over 24, I guess, which 3 over 2, 21 pi over 2, maybe, I think. If not, the previous line is correct. Okay. Anyway, we have completed the integral for right or for wrong here. They have a mistake in the textbook where they, when they got to the point of plugging stuff in, just from one line to the next, they pi over 3 changed into a pi over 6, and then they have the wrong thing plugged in. So like what the equivalent would be if I put square root 3 over 2 here. Okay. So we did it. We did it. Now we have another topic just as long to do. We're going to do surface integrals over a vector field. But first, we want to talk about orientation of surfaces. Okay. So on a surface, right? So like I'll just draw like a sphere or something here. There are two normals, right? There are two normals at every point. I guess there's more if you think about different length, but two normals at every point. One points in and one point out of the surface. Right? So like if you're right here, you can go out. But also the opposite direction, which would point to the interior of the sphere, is also a normal, right? So yeah, so we have that. At least if this is the case, um, then we can talk about the differences between these. So usually there you differentiate between them by saying one is points inside, one outside, or one points up and one down. We can refer to the one we want as inside or outside, or up and down, or something like that, right? There's two different directions. So you can refer to them however you need to refer to them in the problem that they're asking about. Okay. Now, if the surface is closed, like the sphere is, then there's an outside and an inside. So then out is what we call positive orientation. And we call into the surface negative orientation. Okay, so if it's not closed, then there's no inside and outside. But if it is closed, then there's an inward and outward orientation, and positive orientation is out. Okay, so if f if the surface is f z equals f of x y, let's see here, then one normal points upward. That just means has a positive z component. And that one is called positive. And one points downward, vaguely downward, right? Doesn't have to be straight down. Okay. Also, though, in this particular case where z equals f of x y, actually you can simplify your normal calculations, um, because if z equals f of x y, then your parameterization could just be um, r of x y could just simply be x y z of x y. Sorry, f of x y. So that's your parameterization, and then your tx can be calculated just to be 1, 0, whatever partial with respect to x is. Your ty could be 0, 1, and then the partial with respect to y. And then tx cross ty is going to be negative fx, negative fy, 1. So it's always going to be this in the case where z equals f of x, y. Otherwise, then you're going to do this. So it's going to be definition here. Let S be smooth, orientable. That means it has an orientation. Um, orientable surface with parameterization R of UV. Then I'm just going to say the unit normal to the tangent plane is in, so the capital N vector, and it's tu cross tv over magnitude tu cross tv. So it's the normal that we were using before, but we were using tu cross tv before in the previous problem. But now we're talking about the unit normal to the tangent plane, and it's this. Um, so, like, let's see here. Let's just do it like a quick example. Give the upward orientation. And that means they want the in, basically, is what they're looking for. Okay, so give the upward orientation for the surface. So what that means is they want in. Okay, so how would we do that? Right? Well, first you need your parameterization, right? Now we know how to do that actually. Um, right? Because whenever you have z equals f of xy, you just go r of xy is xy and then f of xy, like that. Okay. And you don't even need to compute the tu and the tv, or in this case tx and ty, because it's all actually already worked out for you right here. But I'm just going to do it. But it is worked out for you right here. You can jump straight to this. Um, So like your tu is actually tx, right? So partial with respect to x is 1, partial with respect to x of y is 0, partial with respect to x of xy is going to be y. Ty, partial with respect to y of everything, is going to be 0, 1, x. Okay. Then technically you got to do your tx cross tv. I realize we haven't done any of these, so I'll just do this one. We haven't done any so far, but won't kill us, maybe. So it would be I and then 0, y, 1, x minus j and then 1, y, 0, x uh, and then plus k, 1, 0, 0, 1. So we do these little determinants. So we got here 0 minus y minus j, x minus 0, and then k, 1 minus 0, which is 1. So overall, what do we get? We get negative y I, negative xj plus k, or negative y, negative x, 1, if you write it in that form. Which, if you look up here, should be negative fx, negative fy, 1. So negative fx is negative y, negative fy is negative x, so negative y, negative x, and then 1. So it is what the formula said it was going to be, but we did it. Okay. So our orientation then is going to be to compute the n over this, right? So the orientation is n, and it's Tu cross TV over magnitude Tu cross TV generally. So for us, with x's and y's, it's going to be negative y, negative x, 1 over magnitude negative y, negative x, 1. So it is negative y, negative x, 1 over, and we got to do this. So this is going to be x squared plus y. I don't know why I wrote that. Square root y squared plus x squared plus 1 squared. And there you go. So, I mean, it just is what it is. There you go. And it is oriented upward, by the way, because the y component, sorry, the z component is positive, right? So this right here, this is upward because positive z. So we didn't do anything to make that happen because it just was. But we could have reversed the direction here if we had to. The other normal was positive y, positive x, negative 1. Okay, so let us write this thing down for our next surface integral here. Surface integral of a vector field. All right. So what are we going to do here? Well, I'm just going to define it. So definition. Let f vector field, not a little f, be a continuous vector field that contains, with a domain that contains, and S be an oriented surface with unit normal capital N, the surface integral over F, of F over S is, so how does it look? Double integral S, and then it's F dot ds. So you can tell the difference between the other type of surface integral because of the dot product. And you can tell the difference between a line integral because this is a double integral. So it's a surface integral, not a line integral. So it looks different than f dot dr. And we got double integral over s. The way you actually calculate it, f dot in ds. Okay, now having done this, there's kind of a trick here. So I'm just going to say, look at this. Some math. Watch. Dot, dot, dot. Okay, we're going to do some math. What math are we going to do? We're going to show you how you actually do this. So we've got the double integral over s of f dot n ds. And this is vector s. Now, how do you do that? Well, let's put the stuff in. So the vector field is just the vector field. So we just say f. Dot, you're in. We just talked about how to compute in. It is Tu cross TV over magnitude Tu cross TV, right? That's your in. But then you've got your ds, which that should have been that. Your ds is magnitude Tu cross TV dA, right? Also, I didn't do it, but I'm going to drag this over a little bit to give myself a little bit of room. And we know you have to plug in your parameterization there, right? So what happens is that this and this are simply going to cancel each other out. And what you're going to be left with then is a double integral over just whatever the domain is. This should have already been that of f with your parameterization plugged in, dot product with tu cross tv. Notice there's no magnitude anymore. And then your dA, whatever that is. Okay, so this is how you actually compute that. So that's very important. The double integral over surface of f dot n ds. What you do is you use the formula above. Now, I do want to say something else, which is that this integral is called a flux integral. So kind of a vocab here. Is called a flux integral. And also, just like we did flux in like 2 dimensions, this is going to indicate the rate that fluid flows out of surface or through a surface. So the normal interpretation of this integral is that uh, like if f is like fluid velocity field, then surface integral of f dot n ds, the flux, is the rate fluid flows through the surface f. Right, so very similar interpretation to um, line integrals when we were in vector field, but like a 2-dimensional vector field. So these flux integrals are the same as the flux integrals in section 6.2, but this time we're in 3 dimensions, and we have to do a double integral instead of a single integral. All right. All right. All right. All right. All right. So let's do one, right? Let's get to it, and sooner we do it, sooner we're done. Calculate the surface integral, double integral s f dot n ds, where f, they're going to give us a vector field, negative y, x, 0. And the surface, they're going to give us the parameterization because they're nice. So the surface S is given by R of UV is U, V squared minus U, u plus v. U is between 0 and 3. V is between 0 and 4. Uh, all right. So how would you do this? Well, I mean, the steps are very similar to the ones we've already calculated, right? The only difference is there's going to be a dot product involved. So first thing we're going to do normally is find a parameterization. And I'll say with the correct orientation, like if they tell you one, right? Like notice that this problem doesn't say anything about orientation, and that's because they just gave us the parameterization they wanted us to use. So we're just going to use it. Okay. So find a parameterization with correct orientation. It was given in this problem. Oops. That was given to us. After we do that, we're going to have to calculate that normal vector, right? We're going to have to calculate the TU cross TV. That's actually easier than it was before because we don't need the magnitude. Right? So this, for this type, we don't need the magnitude. And again, that's similar to what we did in line integrals as well. So let us do this, TU cross TV. So we're going to need TU. So we got the parameterization right here, so we're just going to use it. So partial with respect to u is going to be 1, negative 1, 1. Okay. TV is going to be 0, 2v, 1. Okay. Then we need TU cross TV. So TU cross TV. Again, you can go use Wolfram. I guess we calculated the last one and it didn't kill us. Did it? I don't think so. We'll do this one again. And hopefully it won't kill us. Negative 1, 1, 2v1 minus j. 1, 1, 0, 1 plus k 1, negative 1, 0, 2v. I think those are right. So let's do these. I'm going to cheat and just go straight to the triangular bracket notation. So we got negative 1, negative 1 minus 2v. Negative 1 minus 2v, comma. We have 1 minus 0. So 1 minus 0 is 1, but with a negative out front. So that's negative 1. Last component, 2v minus 0. So 2v. Okay, so we have TU cross TV. And then I think we can set up our integral now. So again, the key here is the double integral over S of f dot n ds is going to be a double integral over the domain, whatever that is. F, you plug in your parameterization, and then you do a dot product with TU cross TV, and then dA. So this is not going to be hard to set up or anything. This is going to be easy to set up. I mean, partially because they made it easy to set up. So your F is up here. Let's get dF. Duplicate it, bring it down here. Let me get these together, duplicate them. I just want them together here. All right. So when we plug the parameterization in here, you have negative y. So we're plugging this in for the y. So we're going to have negative v squared minus u, comma, x, which is just u, 0, which is just 0. So this is our f with the parameterization plugged in. Dot product with negative 1. Actually, let me just, that was right. dot product with -1 minus 2v, comma -1, 2v. And then our dA, we got to work out a little bit. So let's move this over. dA, we can do the integral in whichever order we feel like. U or v, they're just constants, right? So looking up here, I see constants 0, 3, 0, 4 for u and v. So let's just go 0, 3, 0, 4 for u and v. All right. So, I mean, you got to do this dot product here. And this dot product is not going to be like super hard or anything. It's just a dot product. So we got 0 to 4, 0 to 3. All right. We got to multiply this by this. Oh, that's sad. So it's going to be u minus v squared. That's this times this, which is -1 minus 2v. Notice that what I did here was I just multiplied the minus in here, which reversed these. Okay, second component is going to be u times -1. Third component is going to be 0 times 2v. Whenever we figure this out, that's going to be du dv. This just has to be foiled, I guess. So we will do that. So u times -1 is -u. U times -2v is -2uv. Then we got -1 times v squared is going to be positive v squared. And then -2v times -v squared is going to be positive 2v cubed. Okay, then we have minus u, and then that's it. So let's see if we have any like terms that we could combine. I do see, let's just kind of put them in some kind of order. Let's do our v's first. So 2v cubed, and then I got a v squared, and then I got a minus 2uv, and then I think I got minus u, which is minus 2u. Okay. All right. So at this point, we set up the integral, and you would just integrate. And that's an easy integral. I'm not going to do it because it's tedious, and we've already been here forever. So let's just say you do that integral. You're going to get an answer, and then I'm just going to say 340. Okay. And then they say, therefore, the flux of F across S is 340, right? And there would be units if this had any kind of units. Okay. Yes. And I think at this point, I'm just going to call it done here. The main thing to keep in mind here is when you're setting up, like everything we did for the other kind of line integrals applies here. The only thing is like when you get to this point, right? Just think about it. There's not much different. This is uppercase f. So this is a vector f instead of a lowercase f, scalar f, but you're still just plugging the parameterization into f, and it's a vector. This before was the magnitude of this, which was a number, but now it's just a vector. So this is a vector, this is a vector. So you just find those two vectors, dot product, and integrate. No square roots anymore, like we did when we had the magnitude. There were square roots involved. Those aren't involved anymore. And overall, this is relatively easy. So the point is that the flux integrals are not harder than the scalar integrals because the dot product is an easy operation. There's no magnitudes involved, and overall, it's pretty easy. Hard part is still parameterizing, and you're just going to have to like look up parameterizations for how to parameterize like spheres and that kind of thing. Okay, I think that's it for now. Good luck on the homework. I think this is the last homework that you have due. Don't quote me on this because you may be watching this in a future semester. All right, that's it for now. Talk to you later.